Welcome. I'll be speaking on the addition of generational enhancements to Shenandoah pauseless garbage collection. I'm a principal engineer at Amazon, and I lead this effort there. I've been there for about 3 years. The first year was largely spent trying to decide that this is what we wanted to work on. The talk will follow this agenda. We'll introduce the notion of pauseless Shenandoah garbage collection, talk a little about why generational extensions are beneficial, and then we'll talk about how we have gone into adding a generational mode into the existing Shenandoah garbage collector. Talk a little about how to decide whether a particular service is appropriate for using generational Shenandoah. And then we'll give some guidelines on how you can get started with using generational Shenandoah. This is not a product-ready technology yet. It's in experimental mode, but we're working towards getting it into production, both within Amazon and to the broader community. So to begin with, this is a slide from traditional Shenandoah and provides a good emphasis on how Shenandoah is different from existing or previous garbage collectors. With Shenandoah, we don't have any long stop-the-world pauses. We have very brief moments of coordination between the garbage collection and the application threads. And these are called coordination points. There's 4 of these during each garbage collection pass. One at the beginning of marking, one at the end of marking, one when we begin to update references, and one when we finish updating references. The phases of traditional Shenandoah consist of identifying the live memory. That's the concurrent marking effort. We choose some subset of the live memory to be collected. So we we look at the regions that have been marked. We find the regions that have a small amount of memory that's live within them, and we say, let's compact those regions. Regions that have a large amount of green live data, we say, let's leave those alone. They're already well populated, well utilized. And this is basically what is known as the garbage first heuristic. It's the same approach used in G1 GC. You collect the regions that are easy to collect because they have little amounts of data that have to be copied. We evacuate those regions into a consolidated region. And then we update the references. Anything that pointed to these objects that have been relocated has to be updated so that it knows where the new location is. I want to briefly compare this with parallel garbage collection. In parallel garbage collection, you have a long stop-the-world phase to do all of the garbage collection. So all these 3 phases that I called concurrent with Shenandoah are now stop-the-world phases. We do the marking while everything is stopped. We relocate things while everything is stopped. And then there's no distinct update routes phase. So this can be hundreds of milliseconds at a time of a pause. I want to make the point that there are at least 2 ways you can compare the efficiency of parallel against Shenandoah concurrent. On the one hand, we say parallel is more efficient because it does not have to coordinate while the garbage collector is working. The service threads are all paused. They're not interfering. They're not shaking hands with the garbage collector. The garbage collector has full control over the whole heap. That makes parallel garbage collection more efficient in that sense than Shenandoah. On the other hand, you have all of your cores dedicated entirely to garbage collection. Garbage collection is notoriously memory bus bounded. Garbage collection is very non-localized. It cannot operate out of the cache very efficiently. So if your system has, for example, some of ours at Amazon have 96 cores, and you've said all 96 cores are required to work on garbage collection and garbage collection only, therefore for the next 300 milliseconds, they're basically not getting any cache benefits because they're only working on garbage collection, and that means they're going everywhere throughout memory in random orders. You're not getting very effective utilization of your CPUs. So in that regard, having a concurrent garbage collector is more efficient and provides higher throughput because you can dedicate maybe 12 cores to garbage collection, and all your other cores can remain focused on the application requirements and using the cache effectively because the application is cache oriented. I also want to look briefly at how Shenandoah compares to G1 GC. With G1 GC, the modes or the phases of execution are very similar to what we have with Shenandoah. With G1 GC, there are young collections and there are old collections. The young collections are stop the world. It does everything with the threads, with the applications stalled. But the global old gen marking is concurrent. So it does the concurrent phase, and then it stops the world to do the evacuation and the updating. And that is typically bounded by 200 milliseconds. That's the default configuration. And you have an option with G1 GC to specify a max pause time. And if you specify a smaller max pause time, it will decide to evacuate less memory, for example. That's the way G1 works. Going back to September 2020, this is during the first year I was at Amazon, we were seeing various services move over to Shenandoah from more traditional garbage collectors like G1 GC. And this is one of those services. And what we're charting here in the different colors is P50, P99, P99.9, and P99.99. And in all of these metrics, you see significant improvement from like peaks of 200 milliseconds down to peaks of about 40 milliseconds, for example, on the 4.9's response time. And that was a very successful adoption. That was not the only one. Same month, another service made that migration. And on their 3.9's latency, they improved from like 90 down to about 35 millisecond response times. So very, very nice progress that we were able to see there. And more recently, just to put this in even more current context, we have seen some groups moving from Shenandoah with JDK 11 to Shenandoah with JDK 17, and right here was an experiment with JDK 17, and you can see the scale is hard to read, so I'm going to zoom in. And basically the only change here is the scale going from 400 on the one below up to 100, so we can see this a little bit better. And if I zoom in one more time, you can see basically that P90, well, let's go with the P99, easier to see here. P99 went from about 10 milliseconds down to about 2 milliseconds. And the reason for this is because with JDK 17, Shenandoah moved to concurrent stack scanning. So that's a huge improvement, and that was universally seen by other services as well. In this case, they rolled this change out because they found some issues with their migration. They didn't properly get everything done for JDK 17, so they've moved now. But that's the data we had at the moment. So based on what I've just told you, I want to kind of summarize. The benefit of concurrent GC is that it reduces GC pauses. But there's some trade-offs here. It needs a larger memory buffer, and I'll explain that in a minute, but the idea is that if we're going to do concurrent garbage collector, we have to start the garbage collection before we're out of memory. So there's some uncertainty and some heuristics required to decide when to start the garbage collection. And we need to have enough of an extra buffer so that we can continue to allocate while we're completing the garbage collection. So we'll dig into that a little bit deeper. But this slide provides some key motivation for why Amazon believes it's important to add generation to Shenandoah garbage collection. So hypothetically, suppose you've got a workload, and these are realistic numbers, but they're not taken from any particular service. Suppose you have a live set of 2 gigabytes. So at any moment in time, your service has to have 2 gigabytes of live memory. And suppose it's churning through ephemeral or temporary memory at a rate of 10 gigabytes per second. Assume that Shenandoah, the traditional Shenandoah without generations, takes a second of concurrent execution time to complete garbage collection. So during that second of time, I'm going to allocate 10 gigabytes of memory. So I need to have a runway of at least 10 gigabytes of memory so that I don't run out during the second that I'm doing my garbage collection. Meanwhile, I have 2 gigabytes live at the start of garbage collection, so I need 12 gigabytes total to finish the first garbage collection. It gets worse, though, because now I have to, as soon as I'm done with the first garbage collection, I have to start another garbage collection. I'm holding 12 gigabytes live right now. Anything that was allocated during the current garbage collection can't be collected until the next garbage collection. It was live during this garbage collection. So I start another garbage collection. It takes me another second, during which I allocate another 10 gigabytes of memory. So now I've got 22 gigabytes of buffer to represent 2 gigabytes of live data. So that's a large amount of heap space. So what generational Shenandoah allows us to do, it allows us to collect the memory much faster. We focus our attention not on the 2 gigabytes that's live, because that's mostly been promoted into old gen. We focus on the memory that's almost entirely dead. And the marking effort is proportional to how much is live within just the young gen instead of within all of the heap. So we can do this young gen collection in much less time than it takes us to do a traditional Shenandoah full mark. For example, quarter a second. So now I can do 4 of these in a second, where I used to do 1 of these in a second. So during the quarter second of a young gen collection, I allocate 2.5 gigs. At the end of the second one, I've got 5 gigs plus my live data, 7 gigs. So it's a 7 gig heap versus a 22 gig heap. So that's the reason that we see value in making generational Shenandoah work. Sometimes we'll use this improved algorithm to shrink our heap size, but we can also use it to simply reduce the CPU effort of garbage collection, or perhaps to give us more flexibility in terms of when we trigger the start of garbage collection. It's much more forgiving if we're operating a little bit further away from the edge of the cliff. Back in 2020, we did some studies on traditional Shenandoah. And we were very much motivated to bring our latencies down. And the nice thing about Shenandoah is the pause times at that time were pretty much guaranteed to be below 10 milliseconds. And G1 GC pause times were measured in the hundreds of milliseconds. But what we were seeing on heavy workloads, we would see that G1 GC was actually providing, if you measured client response times, it was actually providing better client response times in the average and in the maximum than Shenandoah. So Shenandoah max is this number here, always worse than G1 max here. And Shenandoah average here, always worse than G1 average. These are client response times. This is not GC pause times. And this is on a heavy workload, okay? Heavy workload. What does this tell us? Well, Shenandoah just can't keep up with a heavy workload. It needs the generational benefit that G1 has. But we were especially interested in what's going wrong over here. And so we zoom in on that, and I need to explain something about the way Shenandoah works. Shenandoah goes into something they call degenerated mode if it ever fails to replenish the allocation pool before the allocation pool becomes exhausted. So every time you start a garbage collection, it's a race. The garbage collection says, I got to replenish the pool. We're about to run out. The application says, I'm trying to run as fast as I can, which means I continue to allocate objects. If they allocate the last bit of memory and the garbage collector hasn't replenished yet, we degenerate. And this stops the world so that the GC can catch up. So what's happening on that workload at the 768 megabyte heap is we get into this mode of operation where we are experiencing 381 degenerated GCs in 10 minutes of execution time, which is about 10% of our garbage collections are degenerating. We're just losing too many races. And these we're spending, up to 400 milliseconds out of every second in a pause while the Shenandoah stop the world degenerated mode is trying to catch up. So if you go back to what's the motivation for generational Shenandoah, it's to allow us to win these races more often, basically win these races consistently all the time. We did a bunch of studies back then, and what we observed in general was that Shenandoah would deliver on its promise of the low pause time, below 10 milliseconds, under these conditions. Either you have very low allocation rates, and with a low allocation rate, you can have a pretty high memory utilization. You could have 80% memory utilization if you're allocating only like 50 megabytes a second, for example. Or if you have high allocation rates, you need to have very low memory utilization, so maybe less than 5% live. Turns out those are the two modes of operation for a generational garbage collector. The young generation has very high allocation rates. We see up to 10 gigabytes, even higher in some of our services per second. And the young gen has very low memory utilization. By the time you get to the end of a young gen pass, you've got utilization typically below 10%, often below 5%. Meanwhile, the old generation has a very low allocation rate because the allocation rate in the old generation is the rate at which young objects are promoted. That is very low, generally, for most applications. And our goal is to have high memory utilization above 80% in the old gen memory. Both of those modes should work well with Shenandoah. So that's the observation that motivated our design. As we look at priorities of the things that the garbage collector will be doing, We consider the young generation allocations to be critical. Every time a service says, I need memory, we want to get it to it. As soon as we want to get the memory to the application as soon as it requests it. We don't want any pauses there. That's the highest priority thing the garbage collector has to do. Typically has a very high allocation rate. In fact, the old gen promotions are, in the way we've designed this, entirely optional. So if we get to the point where the garbage collector says, hey, I've got an object ready to be promoted, and we discover that the old gen is too full at the moment to receive another promoted object, we'll just say keep that around in young gen for a while longer until we catch up with the old gen collection. But this allows us then to give total high priority attention to the young gen collection. For synergy, for efficiency, and G1 does the same thing, when we start an old gen collection, we basically piggyback on a young gen collection. So the young gen is operating very frequently. Every time we run a young gen, it has to scan the roots. That basically includes all the stack frames of every thread that's running. You could have tens of thousands of threads. That includes the loom threads. Every stack has to be scanned. So when we do this root scan, if we call it bootstrapping old gen collection, then we will keep track of any thread stack pointers to old gen or young gen. If we're doing just a young gen collection, we ignore the stack pointers to old gen. But that's the only difference, whether it's a young gen collection. So this illustrates the typical behavior of a properly configured generational Shenandoah system. So we've got our service threads running without interruption if it's been properly configured. We have these periodic young gen complete collections, which are concurrent, so the threads can continue to run. And between these young gen collections, we will do increments of old gen collections. These increments mean we are concurrently marking the old gen memory. Now, I say this is properly configured. What do I mean by that? The key ideas of proper configuration are, first of all, the heap is large enough to handle whatever the workload is. We have the appropriate number of threads dedicated to garbage collection. We have properly sized the young gen versus the old gen. We have determined the age at which objects should be promoted. Those are the key contributors to proper configuration. Right now, most of those configurations are dialed in manually by experts like ourselves. As I say, this is still pre-production, but we're working on automating the selection of all those configuration parameters. As I pointed out, we do only increments of old gen garbage collection. That's because the old gen effort is much larger than the young gen effort. The young gen has to mark and evacuate the live objects within young gen, but that's probably less than 5% of the size of young gen. It's a very small amount of memory. It runs very fast. The old gen, as I said, it could be equal size. It could be even larger than your old gen, and it's 80% utilized if we've got it well configured. So that's a lot of live memory that has to be marked. And so it takes a long time. It takes much longer than a young gen pass. So that has to be incremental. And it has to be preemptible by the young gen collections. So each time we do a young gen collection, we're going to reclaim all of the objects that were dead at the start of that young gen collection. Anything that is allocated while we're doing the young gen collection will still be live at the end here. That's if it was live during the collection, we can't reclaim it. So the reality is, at the time we finish the young gen collection, a lot of the objects allocated during that span are dead, but they're not reclaimed until here, the end of the next collection. When this guy starts, they're dead, so he can reclaim them. But in the meanwhile, we call that the floating garbage, because it's garbage, but it can't be reclaimed until here. Some small percentage of the objects that are live at the end of young collection will be promoted into old gen. And that's the way the generational garbage collection works. Now, as I pointed out, the old gen effort is making these increments of progress on concurrent marking. At some point, the concurrent marking finishes. It says, I've marked everything in old gen. At that point, the old gen collector says, I'm going to look at all these old regions, and I'm going to decide, I'm going to select some of those old gen regions to be collected. And it builds up a set of collection set candidates. And it does this based on the garbage first G1 sort of heuristic. Basically, it chooses old gen regions that have lower utilization. In young gen, we'll pick regions that are, utilized less than 10%. In old gen, we might pick regions that are utilized less than 65%. We're targeting a much higher utilization for old gen. So then we've finished the old gen effort. It has nothing to do until those candidate collection set regions have been collected. So now every time we start a young pass, we will piggyback some of the regions that were placed in the candidate set by the old gen collection. So now these young efforts are going to take a little bit longer because they're also going to evacuate some subset of the old gen regions that were identified by the old gen effort. These take longer, but now they're not time sharing with the old gen. That's idle until we finish evacuating the entire candidate collection set. Once we have finished with the last of the candidate collection, old gen collection set regions, then we can start another old gen effort. We could start it right here, but we don't have to. We use heuristics to decide when is it appropriate to start another old gen effort based on how the rate at which we're promoting and how full old gen is at the moment. So I've made a lot of mention of the G1 collector, and I want to emphasize there are a lot of similarities between the way Generational Shenandoah works and the way G1 works. So the garbage first heuristic says we will only focus on memory regions that are easy to collect because they have a lot of garbage. We'll collect the garbage where it's easy to find. That is the way G1 works for its old gen. That is the way Shenandoah works for both its old gen and its young gen. Both techniques have mixed evacuations. In both cases, after we have completed a concurrent marking of the old memory, we will do multiple mixed evacuations in order to collect all of that old gen memory. G1 limits the size of the mixed evacuation collection set because each evacuation is stop the world, and they are not allowing themselves to take longer than max possibilities for any single mixed evacuation. So they put a bound on how much they can process in each mixed evacuation. We also limit the size of our mixed evacuation, but for a different reason. Remember, our mixed evacuation is concurrent, so we don't have a problem with creating too long of a pause, but we do want to make sure that we stay on pace. So If we cause the mixed evacuation to take too long, that means the young gen collection will take too long, and it won't be able to replenish the free pool soon enough for the application to get its continued allocation needs. So we limit it so that we don't take too long with our mixed evacuation in concurrent time. The young collections with G1, it's a stop the world effort with the size constrained by the maximum pause time. With G1, it's triggered when memory is exhausted. That's an easier problem to solve than our problem is. We have to trigger it before memory is exhausted. We have to trigger it with anticipation of how fast are you going to continue allocating memory, and we're going to have to pace ourselves so we finish collection before you've allocated all of what remains. G1 has the notion of an Eden and a survivor space. Eden is where we just recently allocated, and then if it's survived one young collection, we assume it will. We move it into a survivor space so that it will age before it gets promoted. Shenandoah doesn't have a specific survivor space, but it has a heuristic that treats certain regions as survivor space. Basically, once you've copied objects from one young region to another young region, that region that holds the consolidation of previously allocated objects will tend to be ignored by subsequent young gen collections because it will have a higher utilization. It won't be in the G1, the garbage first collection set, and it will be ignored until it eventually reaches a promotion age, and then those will be promoted. I've got some data that shows kind of our early results with Generational Shenandoah. This is a P50 response time. It's kind of a modest workload, only 67 megabytes per second. Live memory of about 1.8 gigabytes. So with a 3 gigabyte heap size, that's like 33% here and lower utilizations here. At P50, Gen Shen is kind of in the middle there. What's more interesting is what happens when we go out to the tail latency. So at 4.9 percentile, you see that Generational Shenandoah actually shows benefits over traditional Shenandoah and over ZGC. What we also see, and this is what you would expect to see, G1 and parallel have much higher latencies. And this is, once again, not measuring pause times, but measuring client end-to-end response times. And then at P100, so maximum observed times with 100,000 samples, see very good Generational Shenandoah beating traditional Shenandoah and the alternatives. We've also done we've done a variety of experiments. I'm clearly not showing you all of them, but here we have P50 response latencies at a much higher allocation rate, 444 megabytes per second. So this is, 8 times higher than the previous one. Generational Shenandoah kind of in the pack for the P50. At P49s, you begin to see the benefits and strengths of Generational Shenandoah. Kind of an interesting curve here for ZGC where it does really well, 25% to 14%, but not so well when we get to higher utilizations. Let's see. And this is at the P100, the maximum. Once again, Gen Shen very good here, but beginning to show some degradation compared to traditional Shenandoah under higher utilization. And we understand what some of the issues are. We're addressing them. They come out even more significantly here. this is the highest utilization and allocation rate of the things I've measured. This is Generational Shenandoah hand-tuned. We spent a lot of effort to tweak the configuration to make it work well, but see significant benefits all the way to 4 nines compared to alternative technologies. Then we do a little bit worse in the max pause times. Let me summarize this result by saying it's very promising, the results we're seeing. A few things that we're focusing on. We don't like that we have to hand tune it. That's all going to be automated, and it's going to be adaptive, so that if your workload changes, the configuration will change on the fly. We don't like the fact that we went from a pretty good number here to kind of a bad number here, even worse than G1 in the max pause time. We believe this is a matter of us needing to improve the adaptive behaviors and a general requirement to improve efficiency overall. And we have identified some key areas where we need to focus our attention to make further improvements. I want to make sure you all understand this is not yet production ready. We're not able to support production deployments. We're not able to turn around overnight and fix a bug if you say, hey, we found a bug. We're focusing very much on performance improvements right now, and those are taking weeks or months at a time. And this is not available in the standard Pareto distribution at this time. As I said, our focus is we're starting to look at various real-world workloads with a number of services inside of Amazon. Consistently, we are seeing modest improvements to tail latency under high memory utilization if we invest the effort to hand tune. But these early experiments are very much emphasizing to us the need for automatic and adaptive tuning of the configuration, making some improvements to the GC scheduling and the pacing heuristics, and improving the overall efficiency with particular emphasis on the way we represent the remembered set, which is how do we know that there's a pointer from old gen to young gen. So how we represent that, how we maintain it, and how we utilize that. And we're also looking at some ways to reduce the floating garbage, further reductions. This work at the current time is upstreamed in the GitHub repository for the Shenandoah project. It is not merged with OpenJDK mainline at this time. After we can demonstrate the real value on multiple production deployments, we will begin the process of merging it into mainline OpenJDK. Make sure people understand that Generational Shenandoah, while we can provide guarantees of 1 or 2 millisecond pause times, any service that values response times below 100 milliseconds is probably an ideal candidate for something like this technology. You don't have a lot of other options. The ideal candidate does have a memory set that combines young gen and old gen objects. So your transactions maybe chew through a lot of memory very quickly, but you also have some persistent data that sits around, and that's what generational garbage collection is most ideal for. And finally, I want to make the point that Amazon works at scale. We have tens of thousands of instances in every fleet, and if we can cut the amount of memory that we put on every one of those hosts, that translates to lots of money. It also translates to reduced bills for powering these computers and for cooling the server rooms. So I would invite any of you that are candidate users of Generational Shenandoah to to try it out. As I say, don't put it into production yet, but if you can provide us with feedback that helps identify issues, especially if they're issues we're not already aware of, things that we need to focus our attention on so that it will be production ready and will provide the value that you're looking for, please feel free to reach out to us. There's a suggestion you can open a ticket here so we can communicate with you, and you can get help from us, and you can tell us what we need to do to make it work better for your needs. This is where the source code is, but this is where you can get pre-built binaries that you can run on Linux, and makes it a little bit easier for you to do some experiments if you'd like to. So I think I've got, it says I have 4 minutes for questions. Are there any questions we can entertain at this time? I'd be glad. Yes.
The work in the league at ZGC about generation and garbage collector. It's basically the same target both Shenandoah and ZGC.
So is that a question or it's a comment? So okay, so I'm not sure if I heard everything you said, but so yes, the ZGC is also working on generational mode, and we have had some conversations with them. We try to share our results. We're really most interested in making sure there's a high quality pauseless garbage collector that is very efficient for the use of our customers. For any of our customers that are better served by Generational ZGC, that's great. And we have some services inside Amazon that are using ZGC today. And we've also been doing experiments to compare ZGC generational to our generational mode. In both cases, they are ongoing development projects. So my sense is that they're targeting a slightly different audience than we are, but it's good that both efforts are going. Yeah. Any other questions? Yes.
How do you differentiate old gen and young gen?
So the question is, how do we tell the difference between old gen and young gen? So we use a regional garbage collector. So certain regions are identified as being dedicated to old gen or affiliated with old gen, other regions with young gen. So all objects are allocated in young gen after they have survived a certain number of, and it's configurable, young gen collections without being collected. We say, okay, you're going to be moved, so we evacuate it into an old gen region. So once it's in that region, that object is considered to be an old object. Does that answer your question? Yes?
Do you perform experiments of several hundred gigabytes?
Yeah, so the question is whether we look at, so I did experiments here with 8 gigabytes or something. The question is whether we look at several hundred gigabytes. Yes, we have one of our services we're working with has like a 640 gigabyte heap or something like that. Yes, it's also very much relevant.
Because we are waiting for that with heaps Shenandoah GC.
Yeah, so that's good. I mean, you would be an ideal candidate. Let me just qualify that. We don't yet have very much special consideration for NUMA sockets. So, I mean, it may work well for you, but we have in mind a long list of things that we want to do to make it work better on NUMA that we haven't yet gotten to. Officially, I'm out of time. I guess I would be glad to take other questions if people want to ask me here, but I should let the next people set up. Okay, thank you.